Ever stop to think about the magic powering the device you're holding, the servers humming in vast data centers, the advanced systems in your car? It's all thanks to something so small it's almost unimaginable: semiconductors. And at the very heart of this invisible revolution stands one company, arguably the most important factory on the planet, Taiwan's Semiconductor Manufacturing Company, or TSMC. They're the silent giants behind roughly 90% of the world's most advanced computer chips. Now, TSMC has just dropped a bombshell, announcing a new technology that promises to take us beyond the 1 nanometer barrier. As someone who spent years immersed in the intricate world of chip design, let me tell you, this is not just an incremental improvement. It's a monumental leap forward for the entire tech industry. So, buckle up as we dive deep into the ingenious science behind this breakthrough. Explore the next frontier in semiconductor technology, dissect the recent movements in TSMC's stock price, and uncover why the future might see us relying less on the ultra-precise, yet incredibly complex lithography machines from ASML. Think back to 1987, when TSMC first opened its doors. Their initial offering, chips manufactured using a 3-micrometer process. Now, a micrometer is 1/millionth of a meter, which translates to a whopping 3,000 nanometers. Fast forward to today, and TSMC is ramping up production of chips using a 1.6 nanometer technology. Just let that sink in for a moment. Over the past 4 decades, they've managed to shrink the critical dimensions of their chips by an astounding 99.99%. And the next game changer is already on the horizon, driven by innovative new materials and a revolutionary transistor architecture called CFET. But to truly appreciate the brilliance of this upcoming era, we need to first understand the fundamental building blocks of all silicon chips: transistors. Let's take a journey back to around 2012. Up until that point, the workhorse of the semiconductor industry was the planar transistor. What made the planar transistor so successful for so long? Its elegant simplicity. Imagine a tiny electronic switch, a gatekeeper controlling the flow of electrical current. Think of a water pipe with water rushing through it. If you place a valve in the middle, you can easily turn the water flow on or off. A planar transistor operates on a remarkably similar principle, but with electrons instead of water. It has 3 key components: the source, where the electrical current originates, the drain, where the current exits, and the gate, which acts as our valve, used to control the transistor's state. When a voltage is applied to the gate, it generates an electric field. This field either creates a conducting path, allowing electrons to flow freely between the source and the drain, the on state, or it blocks this path, preventing current flow, the off state. This straightforward design made the planar transistor relatively easy to understand and manufacture, and it served as the cornerstone of our digital world for nearly half a century. However, as our insatiable demand for more powerful and energy-efficient electronics grew, the pressure to shrink the dimensions of these planar transistors intensified. By the time we were approaching the 22 nanometer process node, we started hitting fundamental physical limits. The magic of simply making everything smaller began to falter. One of the biggest challenges was the gate length, the distance between the source and the drain that the gate controlled. For a long time, reducing this gate length was the primary way to make transistors faster and pack more of them onto a chip. But as the channel became increasingly thin, a problematic phenomenon called electron tunneling started to occur. Imagine our water pipe analogy again. You close the valve tightly, but you still see water seeping through. In the transistor, even when the gate was supposed to be in the off state, electrons were quantum mechanically tunneling from the source to the drain. This unwanted leakage of current was a major problem because it meant we could no longer reliably control the transistor. It was like having a leaky faucet in every single switch on the chip, wasting energy and generating heat. As we'll see, This challenge marked a turning point, shifting the focus of innovation squarely onto the design and control of the gate itself. The first significant step in this evolution was a clever architectural innovation called the FinFET, which emerged around 2012. Instead of a flat planar channel, engineers started to stretch the channel into a three-dimensional fin-like structure, standing vertically on the silicon wafer. The genius of the FinFET was in how it addressed the gate control issue. Instead of just having the gate on top of the channel, it now wrapped around three sides of the fin, the top and both sides. Think of it as having a more encompassing grip on the flow of electrons. This enhanced gate control was an incredibly elegant solution. By having the gate on three sides, it could more effectively turn the transistor on and off, leading to faster switching speeds and allowing us to cram even more transistors into the same area of silicon. Suddenly, the seemingly insurmountable barrier of electron tunneling was being overcome. What's fascinating is that Intel was actually the first to bring FinFET-based chips to market in 2012 at the 22nm process node. Just a year later, TSMC also transitioned to FinFET technology, recognizing its transformative potential. In fact, today, almost all high-performance electronics, from the powerful Apple Silicon chips in iPhones and Macs to the cutting-edge GPUs from NVIDIA and AMD, are manufactured using FinFET technology. It became the undisputed champion of the semiconductor world for over a decade. But the relentless march of progress never stops. As of today, the limits of the FinFET architecture are being reached. The industry is once again standing at a precipice, poised to take another bold leap in transistor design. We are now entering the truly three-dimensional era of transistors, and remember, it's still all about the gate. If you think about it logically, the only way to shrink the footprint of a transistor further and achieve even better control over the flow of electrons is to exert that control from even more sides. This is where the next wave of innovation, centered around gate-all-around, GAA, transistor architectures, comes into play. The core idea is ingenious. Instead of having vertical fins with the gate wrapping around three sides, we're now turning the channel on its side and stacking horizontal nanowires or nanosheets. Imagine taking those vertical fins and laying them down horizontally, one on top of the other. Now, the gate can completely surround each of these nanosheets, offering truly exceptional electrostatic control and virtually eliminating leakage current. Instead of the channel growing horizontally across the wafer, we're now multiplying the channels vertically, stacking them like incredibly thin layers. This design allows the gate material to fully encircle the channel from all four sides, creating a true gate-all-around structure. This complete embrace by the gate provides unparalleled control over the electrons flowing through the channel, drastically reducing leakage when the transistor is off and enabling faster switching speeds when it's on. The good news is that the first gate-all-around transistors are already here. TSMC's N2 technology, which utilizes GAA transistors, is entering mass production, and we can expect to see the first devices powered by this technology, potentially including the next generation of iPhones. This marks a significant milestone in the ongoing quest for smaller, faster, and more energy-efficient electronics. Now, let's talk about the tools of this revolution. While the transition to gate-all-around architecture is an evolutionary step from FinFET, building upon decades of expertise where TSMC has been a leading force, many manufacturing processes need to be fundamentally re-engineered and fine-tuned. And here's a significant shift we're starting to see. From now on, extreme ultraviolet EUV lithography machines, while still incredibly important, might become less of a bottleneck, less on the critical path for future advancements. Instead, other specialized tools and novel materials will play an increasingly vital role. Think of EUV lithography as the ultimate high-precision printing technology for the nanometer scale. These machines essentially create a controlled, tiny explosion inside a vacuum chamber. This explosion generates extremely high-energy photons with an incredibly short wavelength of 13.5 nanometers. These photons are then carefully directed and focused using complex mirrors to pattern the intricate features of a chip onto a silicon wafer coated with a light-sensitive material called resist. It's a breathtakingly complex process, often compared to tiny star explosions, because the underlying physics involves the creation of extremely hot plasma, similar to what happens in the sun. For years, as we push the boundaries of transistor size, EUV lithography has been absolutely crucial for defining the smallest features, particularly the intricate interconnects that link the billions of transistors on a chip. However, when we look at the gate-all-around architecture, the primary challenge shifts. It's no longer just about printing incredibly fine lines. The real magic lies in the precise creation of those horizontal nanowires or nanosheets, and then uniformly wrapping the gate material completely around them, especially when you can't directly see the underside of these incredibly tiny structures. This is where atomic layer deposition, ALD, and epitaxial growth techniques become absolutely critical. ALD is like painting with atoms, allowing for the deposition of extremely thin and uniform layers of materials, one atomic layer at a time. Epitaxial growth, on the other hand, is a process where a thin crystalline layer is grown on top of an existing crystalline substrate, with the new layer adopting the crystallographic orientation of the underlying material. In the context of GAA transistors, it's crucial to precisely deposit the gate dielectric, the insulating layer between the gate and the channel, and the metal gate material around these intricate nanosheet structures with atomic-level precision. And here's where the landscape of key equipment suppliers broadens. While ASML dominates the EUV lithography market, companies like Applied Materials and ASM, not ASML, a different company entirely, possess the secret sauce and the leading technologies for these crucial deposition steps. They have the expertise in designing and manufacturing the specialized equipment needed to perform these atomic-level manipulations with the required uniformity and control. But the process doesn't end with deposition. After creating the stack of nanosheets and depositing the initial gate materials, we need to precisely remove the material in between these channels to isolate them and allow the gate to fully wrap around each one. This is where specialized etching techniques come into play. Lateral etching tools, often supplied by companies like Lam Research, are critical for this step. They can selectively remove material in a horizontal direction, creating the necessary gaps between the stacked nanosheets without damaging the delicate structures themselves. Finally, we need one more deposition step to fully form the gate around the exposed channels, ensuring complete electrical contact and control. Again, tools and expertise from companies like Lam Research and ASM are vital for this final, critical stage. So, while EUV lithography remains a sophisticated and indispensable technology for many aspects of chip manufacturing, the advent of gate-all-around transistors signals a relative shift in emphasis. The ability to precisely deposit, grow, and etch materials at the atomic level becomes paramount for realizing the full potential of these new architectures. This elegant solution behind today's state-of-the-art gate-all-around transistor architecture is fundamentally about moving in the vertical dimension, stacking channels to increase density and enhancing gate control. And this vertical stacking is what will enable us to continue shrinking transistors beyond the 3 nanometer node. It's fascinating to reflect on the pace of innovation. We had planar transistors as the dominant technology for roughly 50 years, a true workhorse of the digital age. Then came FinFET, which reigned as the state-of-the-art for about a decade, a crucial stepping stone into the three-dimensional realm. Now, after roughly 30 years of research and development, Gate-all-around transistors are finally entering mass production. How long will this architecture last as the leading technology? Given the accelerating pace of innovation, perhaps only 5 years or so. This is just one of many examples where we see technological progress accelerating at an almost dizzying rate. As the visionary Ray Kurzweil famously said, "We won't experience 100 years of progress in the 21st century. It will be more like 20,000 years of progress at today's rate." I totally feel that sense of exponential growth, don't you? And speaking of things happening faster than ever, we all know that artificial intelligence is now helping us create things at an unprecedented speed. One of the most exciting shifts is occurring in software development. What if I told you that I managed to create a custom-made web app with just one click, without writing a single line of code? With Hostinger Horizons, you can turn your bright ideas into fully functional web applications using AI-generated code. No more wrestling with complex coding languages, no complicated deployment processes, and no need for third-party hosting. Just a couple of clicks, and your app can be live and ready for the world. Here's how this incredible tool works. Simply type your web app concept into the AI chat box, describing what you want it to do and how you envision it. Then, watch as the AI instantly generates the first version of your application. It's like having a coding assistant that understands your vision and brings it to life in seconds. And if you need any tweaks or further refinements, the AI assistant can quickly make edits based on your feedback. Once you're satisfied with your creation, you can instantly publish your app, complete with a domain name. The possibilities of what you can achieve with Hostinger Horizons in just a few clicks are truly mind-blowing. So, whether you're a seasoned entrepreneur like me, a budding founder with a great idea, or looking to launch a micro-SaaS startup, Hostinger Horizons provides an all-in-one solution to build and deploy your software with remarkable ease and speed. On top of this incredible platform, Hostinger offers a generous 30-day money-back guarantee, so there's absolutely no risk in giving it a try. Use my special link in the description below and apply my code to get a fantastic 10% off your first month on Hostinger Horizons. Thank you, Hostinger, for sponsoring this episode and empowering creators like me to bring their digital visions to life faster than ever before. Now, having explored the current state of the art with gate-all-around transistors and emphasized the crucial role of gate control, let's delve into the most exciting part, the next big thing in semiconductors. How can we possibly build even smaller and faster transistors beyond the advancements of GAA? What's the next architectural leap? Interestingly, TSMC is currently pursuing two parallel tracks of innovation, one focused on vertical scaling and the other on exploring revolutionary new materials. Let's start by examining the vertical approach. The ingenuity of this new architecture lies in the intricate details of a novel stacking method. Instead of placing individual transistors side by side on the silicon surface, the new architecture involves vertically stacking a p-type metal oxide semiconductor, PMOS, transistor on the bottom and an n-type metal oxide semiconductor, NMOS, transistor on top. This clever vertical arrangement effectively cuts the transistor's footprint in half for a given level of performance, providing a pathway to keep Moore's law, the historical trend of doubling the number of transistors on a chip approximately every 2 years, alive and kicking. This innovative architecture is called CFET, which stands for Complementary FET, field effect transistor. While other companies might use different names, the fundamental concept remains the same. The next major evolution in semiconductor technology is the move towards truly vertical transistors. In this CFET structure, the bottom layer houses a p-type gate-all-around transistor, known as a PMOS. When a negative voltage is applied to the gate of a PMOS transistor, it creates a channel of positively charged holes, allowing electrical current to flow. Conversely, The top layer contains an N-type nanosheet transistor, an NMOS. Here, a positive gate voltage creates a channel of negatively charged electrons, enabling current flow. Crucially, both the NMOS and PMOS nanosheets are completely surrounded by the gate material, forming a gate-all-around structure for both types of transistors. These nanosheets are incredibly thin, typically just a few nanometers in thickness, and narrow, around 10 to 15 nanometers in width. What's particularly noteworthy is that one of the key figures spearheading the development of CFET technology at TSMC is Dr. Shuya Liao. As a director of device architecture pioneering groundbreaking innovations at TSMC, she joined the company in 2021 after an impressive 16-year tenure at Intel. During her time at Intel, she made significant contributions to all the latest process technology developments, from the 65-nanometer node all the way down to the 4-nanometer generation. Now, at TSMC, she is at the forefront of developing next-generation device architectures like CFET, while simultaneously exploring the integration of novel materials into future transistors, which we'll discuss in more detail shortly. Her recent research paper details the first functional CFET device developed by TSMC, a truly remarkable achievement that signifies a major step towards the next era of semiconductor scaling. Recently, at the latest International Device Manufacturing Conference, TSMC presented their progress on this front, showcasing a working CFET device and highlighting their innovative solutions to the complex challenge of interconnecting the bottom and upper transistors in this vertical structure. It currently appears that TSMC is leading the charge in CFET development, seemingly ahead of competitors like Samsung, Intel, and even the renowned research institute IMEC. However, the CFET architecture, while offering significant density advantages, comes with its own set of formidable challenges, particularly in the area of interconnect complexity. You know, those incredibly tiny, hair-thin metal lines that weave their way across a computer chip, connecting the billions of transistors and other electronic components. These interconnects form an intricate, multi-layered network, often with up to 20 metal layers, that enable the seamless transfer of data and the distribution of power across the entire chip. In traditional modern chips, these interconnects primarily run in horizontal layers across the silicon surface. Now, with the vertical stacking of transistors in the CFET architecture, these crucial connections must also extend vertically, linking the PMOS transistor at the bottom to the NMOS transistor at the top, and then connecting these paired structures to the horizontal interconnect layers above. This introduction of vertical interconnects significantly increases the resistance and capacitance in the circuit, which can lead to additional signal delays, slowing down the overall performance of the chip and increasing power consumption. Furthermore, adding these complex vertical interconnects necessitates more intricate manufacturing processes, introduces new alignment challenges during fabrication, and creates potential points of failure or defects in the wiring. It will likely require the implementation of backside power delivery, a technique where power is supplied from the back of the silicon wafer, and potentially even backside signaling for the PMOS transistor to alleviate congestion on the top layers. Not to mention the extreme thermal challenges that will arise with this new architecture. Even now, high-performance NVIDIA GPUs can generate several hundreds of watts of power per square centimeter of silicon, and projections suggest this could reach a staggering 1 kilowatt per square centimeter in the near future. Now, imagine concentrating that immense power into a tiny, multi-layered transistor structure that's part of a densely packed 3D chip package. It's going to get incredibly hot. So, while the CFET approach to scaling is undeniably ingenious in its concept, it introduces a whole new set of manufacturing complexities and challenges, potentially leading to more processing steps and higher manufacturing costs. At the moment, mass production of CFET-based chips is expected to be roughly around 2030, and this breakthrough will indeed allow us to scale transistors beyond the limitations of the 1 nanometer node. As we've seen, in the early days of transistor development, innovations were primarily focused on the geometry and physical dimensions of the devices, making them smaller and smaller. But now, the focus is demonstrably shifting. While continuing to refine transistor architecture, TSMC is also heavily invested in the research and development of new materials, with a particular emphasis on two-dimensional 2D materials. The ultimate goal is to use these novel materials in the channel of the transistor. You might recall that earlier in our discussion, we touched upon the challenges encountered when trying to further shrink the gate length of planar transistors. This limitation is inherent to silicon, the traditional workhorse material of the semiconductor industry. That's why researchers are now exploring alternative materials with potentially superior electrical properties to push the performance boundaries even further. It turns out that certain 2D materials, which are essentially materials composed of a single layer of atoms, exhibit remarkable properties. They can be more robust to the effects that cause leakage current in ultra-thin silicon channels, and in general, offer potentially better electrostatic control. TSMC is particularly focused on a class of 2D materials known as transition metal dichalcogenides, TMDs. You'll see some examples of these fascinating materials displayed on the screen now. These materials hold the promise of enabling transistors with channels that are only a single atom thick, offering the ultimate in miniaturization. However, it's important to note that these 2D material-based transistors are still largely in the research and development phase and are quite some time away from widespread commercial application. The primary bottleneck hindering their mass production lies in the complex growth process of these materials. Currently, they are typically grown as thin films on sapphire wafers and then painstakingly transferred to silicon wafers for integration into existing manufacturing processes. This transfer process is not easily scalable for high-volume manufacturing. To truly unlock the potential of 2D materials in semiconductors, researchers and engineers need to develop methods to grow these materials directly on silicon wafers with high uniformity and yield. In fact, I've dedicated several past episodes on this channel to the exciting world of semiconductor material innovations, covering topics like 2D materials, indium selenide, graphene, and other promising candidates for next-generation transistors. So if you haven't already, make sure to subscribe to the channel now so you don't miss out on these deep dives into the future of semiconductor materials. Another significant shift worth highlighting in our discussion is this increasing emphasis on material innovations. Looking at TSMC's upcoming N2 process node, and considering all the architectural advancements we've just explored, it's clear that the balance of innovation is tilting away from purely lithography-driven scaling and towards advancements in materials science and novel processing techniques. To be clear, EUV lithography tools will undoubtedly remain crucial for many aspects of chip manufacturing, particularly for patterning the dense interconnect layers. However, what I mean is that they might become less of the absolute critical bottleneck, the singular enabler for future transistor scaling, compared to the advancements in materials and transistor architectures like CFET. Over the past few years, there's been a significant focus and discussion around EUV lithography machines, and for good reason. They have been absolutely pivotal in enabling the incredible shrinking of transistors. As transistors became smaller and smaller, the interconnects, the intricate wiring that connects these transistors to form logic gates and other functional units, also had to scale down proportionally. In fact, for a long time, transistor scaling was outpacing the ability to effectively scale the interconnects. Let's take the transition from, say, the 7 nanometer to the 3 nanometer process node as an example. EUV machines were arguably the most critical tool for this scaling because older deep ultraviolet (DUV) lithography machines, which use light with a longer wavelength compared to EUV, simply didn't have the resolution to accurately pattern the finest metal lines needed for the increasingly dense interconnect layers. However, when we look at the latest process nodes, such as TSMC's N2 and the future directions like CFET, the relative importance of EUV for pure transistor scaling might see a slight decrease. This is partly because the challenges associated with these new architectures, like the vertical stacking and gate-all-around structures, place a greater emphasis on advanced deposition and etching techniques, as we discussed earlier. Additionally, the industry is increasingly looking towards innovative solutions like backside power delivery, which could actually reduce the congestion of interconnects on the top surface of the wafer. This shift towards backside power delivery represents a significant change in how chips are designed and manufactured. Until now, all the metal layers responsible for both signal transmission and power distribution have been placed on the top side of the wafer, alongside the transistors themselves. The fundamental idea behind backside power delivery is to move the power delivery network to the back of the silicon wafer. Since the metal lines used for power distribution need to be relatively thick and wide to minimize resistance and deliver sufficient current, placing them on the backside frees up valuable real estate on the top side, where the much finer and denser signal interconnects reside. This separation of power and signal networks can lead to several advantages, including reduced power noise, improved signal integrity, and potentially even higher transistor density. Importantly for our discussion about EUV, moving the power delivery to the backside could also reduce the number of extremely fine-pitch metal layers required on the top of the wafer for interconnects. This, in turn, could mean fewer critical exposure steps requiring the expensive and complex EUV lithography and fewer EUV masks, potentially leading to lower manufacturing costs for certain layers. So, while ASML's EUV tools remain indispensable for pushing the boundaries of feature sizes in many areas of chip manufacturing, the combination of new transistor architectures like CFET and innovative techniques like backside power delivery suggests that the future roadmap for semiconductor scaling might become less solely reliant on advancements in EUV lithography alone. TSMC, however, remains the linchpin, the most critical fabrication facility that the entire global technology ecosystem depends upon. Given TSMC's central role, you might be wondering about the recent performance of its stock. Over the past few months, the stock price has seen a dip of around 15%. What are the factors contributing to this? One of the key concerns weighing on investor sentiment is the potential for the United States to impose tariffs on computer chips, with some discussions suggesting tariffs as high as 100%. While these are currently just proposals and the actual implementation and extent of such tariffs remain uncertain, they understandably create apprehension in the market. In my view, this could be part of a broader strategy by the U.S. government to incentivize companies like TSMC to establish and expand their advanced manufacturing facilities within the United States, aiming to bolster domestic chip production and reduce reliance on overseas sources. This geopolitical maneuvering and the associated uncertainty can often lead to fluctuations in stock prices. However, I personally see this recent dip as a potential buying opportunity. Despite these concerns and the macroeconomic headwinds, TSMC continues to demonstrate robust financial performance. Their recent earnings reports have shown strong revenue growth, with year-over-year increases of around 43%, indicating a continued strong and resilient demand for their advanced silicon chips across various sectors. When you consider the immense capital expenditure required to build and operate cutting-edge fabrication facilities, along with the continuous investments needed to upgrade equipment and stay at the forefront of process technology, it's perhaps not surprising that fewer and fewer companies are able to compete at the leading edge. Back in 2007, there were around 12 major fabrication companies manufacturing chips at the 45-nanometer process node. Today, that number has dwindled to just two, primarily TSMC and Samsung, consistently fabricating silicon at the most advanced 3-nanometer node. And with both Samsung and Intel recently facing challenges in achieving the desired yields at these leading-edge nodes, TSMC's dominance and reliability become even more pronounced. The role of this company in the modern global economy is truly undeniable. Reinforcing this commitment to expansion, TSMC recently announced ambitious plans to invest another $100 billion over the coming years to expand its semiconductor manufacturing footprint in the United States. For once, we're seeing billions of dollars flowing into the U.S. for advanced manufacturing, which is a significant and positive change in trend. This substantial investment will be directed towards building 3 additional advanced fabrication plants, 2 state-of-the-art packaging facilities, recognizing the crucial role of advanced packaging in enabling the performance of high-end chips like those used in AI and high-performance computing, and a new research and development center. As you might already know, TSMC is currently in the process of constructing 2 advanced chip manufacturing plants in Arizona, with the first one slated to begin production as early as this year, and the second one planned for 2027. These are not small facilities. The scale is hard to even comprehend. The total area of these fabs is estimated to be around 1,100 acres, roughly equivalent to 650 football fields, making this manufacturing complex one of the largest semiconductor production sites in the world. Ultimately, whether due to potential tariffs or the higher operating costs associated with manufacturing in the U.S., it seems likely that the cost of TSMC's leading-edge chips will increase in the future. I'd be curious to hear your thoughts on this. What do you think about the potential impact of these factors on the cost of our electronics? Let me know in the comments below. As the brilliant Stephen Hawking once said, we are standing on the threshold of a brave new world. What we choose to do with our scientific discoveries and technological advancements will profoundly shape the future of humanity. It's abundantly clear that the next decade in technology will be heavily defined by the rapid advancement and widespread adoption of artificial intelligence and the continued growth of high-performance computing. Both of these domains demand exponentially increasing amounts of computing power. However, we are already starting to bump up against a critical bottleneck: energy. We are rapidly approaching the limits of what our existing power grids can deliver and what our current cooling systems can effectively handle. Without significant breakthroughs in energy-efficient transistor technologies, our massive data centers, the workhorses of the digital age and the engines powering AI, will inevitably hit a power ceiling, hindering further progress. This underscores the urgent need for the development and integration of novel materials and significant breakthroughs in semiconductor technology to keep pace with the insatiable power demands of artificial intelligence. I believe the solution won't be a single silver bullet, but rather a complex and multifaceted approach. This will likely involve the synergistic integration of novel semiconductor materials with superior electrical properties, groundbreaking new transistor architectures like CFET that offer higher density and lower power consumption, advanced integrated cooling technologies embedded directly within the chips, the adoption of backside power delivery to improve power efficiency, and signal integrity. The increasing use of chiplet architectures connected by high-speed photonic interconnects to create larger and more complex systems, and sophisticated advanced packaging techniques to bring all these disparate components together in a highly efficient manner. It's a grand engineering challenge that requires innovation across the entire spectrum of semiconductor design and manufacturing. What are your thoughts on this? What do you see as the biggest hurdles and the most promising solutions in meeting the ever-increasing power demands of future technologies? Share your insights in the comments below. I'm always eager to hear your perspectives. Before you leave, I want to sincerely thank you for joining me on this fascinating journey into the world of semiconductor technology. I wish everyone health and happiness. And if you enjoy this in-depth content and want to stay up to date on the latest technological advances, be sure to subscribe to the channel and share it with as many people as possible. And if you find this video useful, check out more related videos on my channel. Your dedication and curiosity are what drives this channel. Thanks again for watching. Until next time, stay curious, stay informed. Enjoy.